So I'm going to be talking about 6.1 now. Definition of a linear transformation. So first, let's do a definition. Let's let V and W be vector spaces. Let's review what a function is, okay? Or in other words, a mapping. A mapping, or function, from V to W is a rule that assigns to each vector V in V precisely one vector W, which we call T of V. Okay, in W. We denote the mapping as follows. So I know you guys are used to seeing f as a function, but we are actually going to be using t as a function that maps from one vector space to another. You'll see why we use the letter t soon enough. So as an example, the following are all mappings. First, I want you to imagine the mapping that goes from n by n matrices to the real numbers given by, you take any matrix and you take its determinant. This is a mapping, right? Because it takes a matrix, right? It takes something from M and R and then assigns it a number, which in this case is the determinant. What about this one? T going from M and R to M and R given by, so this time we're mapping a matrix to a matrix, and we're going to do that by taking A and sending it to A transpose. That's an example of a mapping. Let's keep going. How about the map that takes P1 of R to P2 of R? This is first degree polynomials or less to second degree polynomials or less, given by, so I have to tell you where it sends a polynomial, so it takes this polynomial and sends it to sorry, I should have put a 3 there. Okay, so this is an example of a mapping, right? Because I took a first degree polynomial and it mapped to a second degree polynomial. Let's do one more here. How about a map which takes a function to a real number? And how could I do that? Well, here's an example map. I could take any function and send it to the following integral. I could integrate from a to b, f of x dx. So these are all 4 examples of mappings. However, mappings are not what we're going to be focusing on. We care about mappings, so as a note, mappings of vector spaces aren't useful unless they preserve the operations of the space. Okay, so because of this, I need to define a special type of mapping called a linear transformation. And this is the whole point of this chapter, is to study linear transformations. So let's go ahead and define linear transformations on the next slide here. So definition. Let's let V and W be vector spaces which use, what we're going to say is that they have to use the same scalars. So, which use the same scalars. This just means that the scalars come either from the real numbers on both or complex numbers. But we want to assume, usually we assume that it's real numbers. So let's just say that V and W are both real vector spaces. A mapping T, which goes from V to W, is called a linear transformation. Okay, sometimes I abbreviate linear transformation with LT, so just to keep that in mind. We call it a linear transformation from V to W. Every linear transformation maps from one vector space to another. So what is the definition? So we're going to say if it satisfies the following 2 properties. So for all U and V in V, and for all scalars C, the following 2 things have to be true. First, T of U plus V is equal to T of U plus T of V. Before I go on, what exactly do I mean by this, right? Do you guys understand what I'm saying here? The reason I wrote a plus subscript V on the first one and a plus subscript W in the second one is because this addition is happening in two different vector spaces. On the left, we're saying let's add u and v together in the v vector space, and then we take the t of that, so we apply the map. And on the other side, we're actually taking t of u, which sits in w, and t of v, which also sits in w, and then we're adding them over in w. So in other words, the same result has to pop out whether you add them and then apply t, or whether you apply t to each of them and then you add them in the other space. So that's property 1. Property 2, t of c times u is equal to c times t of u. Now again, what this is saying is that if you do the scalar multiplication first and then apply the map, you get the same answer as applying the map to u first and then multiplying. So this scalar multiplication is happening in v over here, and over here the scalar multiplication is happening in w. Okay, now I'm going to write the subscripts here just to avoid confusion. Okay, these have a name, guys. These are called the linearity properties. You can also call them the linearity axioms, okay? But the point is that you need both of these things to be true in order for it to be a linear transformation. Okay? So let me write a couple of notes about this, because a little bit of terminology from functions definitely carries over here. So note number 1. For a linear transformation, t, which goes from v to w, v is called the domain of t, and we don't use the word range in this class, but we are going to use the word codomain. And w is called the codomain of t. Okay, so this is what domain and codomain are. They just specify which vector space you're coming from and which one you're going into. Note number 2. Which of the 4 mappings we listed before are linear transformations? Okay, because they're not all linear transformations. So what about the first mapping? If you recall, the first mapping was, remember, t of any matrix is equal to the determinant of that matrix. Okay. Well, actually, this one is not a linear transformation. Why? Because it fails the first and second linearity properties, right? Because t of a plus b, in other words, that's the determinant of a plus b. We know that that's not equal to the determinant of a plus the determinant of b. So in general, that is not true. So it fails property 1, and just to be complete here, it also fails property 2, because if I multiply it by a scalar, in other words, if I do the determinant of k times a, this is actually equal to k to the n times the determinant of a. We remember we learned this before with determinants. So, in other words, this is not equal to k times the determinant of a, which is kt of a. Right? So both properties fail for the map number 1 that we said. Okay? What about the others? The second map, remember what that one was? That was T of A equals A transpose. This guy is a linear transformation. It actually passes both properties. Both properties hold. What about map number 3? Map number 3, yes, it is a linear transformation. And finally, map number 4. Map number 4 was the integral one. T of f is equal to the integral from a to b of f of x dx. This guy is a linear transformation. Why is that? Well, what's t of f plus g? This is going to be the integral of f of x plus g of x, and we know that we're allowed to split the sum of two integrals up, so this is equal to the integral from a to b of f of x dx plus the integral from a to b of g of x dx. This is just from calculus, but this is the same as t of f plus t of g. Okay, so that's linearity property 1, and you can easily check the other, right? T of k times f is equal to the integral from a to b of k times f of x dx. But we know that we're allowed to pull k out, right? Because it's just a constant. And this is just k t of f. Okay? So it is a linear transformation. Let's do another example of checking whether something is or is not a linear transformation. So let's define T, which maps C1 on an interval to C0 on an interval, given by T of a function f is equal to f prime. In other words, T is just taking a derivative. Question, is T a linear transformation? Okay, well, we need to check linearity properties. So let's let f and g be in our vector space. And let's let k be a real number. Okay, let's check property 1. What is T of f plus g? This is just going to be f plus g prime. And we know from calculus that when you take a derivative of a sum, this is just equal to the sum of the derivatives. Okay, but this is just T of f plus T of g. In other words, property 1 holds. Let's look at property 2. What would T of k times f be? This is equal to k times f prime. And what is the derivative of a constant times a function? We know that constants can pull out, right? So this is just k f prime, which is the same as k t of f. Okay? So since both properties hold, so since the linearity properties hold, T is a linear transformation. Okay, something to say here about this. We can condense the linearity properties of a linear transformation into one step. So this leads us to a theorem. Let T going from V to W. This guy is a linear transformation if and only if T of C1V1 plus C2V2 is equal to C1T of V1 plus C2T of V2. This might look familiar to you. This is actually sort of like combining both properties. Okay, combining both linearity properties. So this is all you have to check. This could save you time if you're trying to check, but I would recommend just sticking with the two main axioms, okay? Now, let's look at linear transformations a little more closely. Recall that if we have a basis and the basis is V1 to VK for a vector space V, then this means you could take any vector. So this means for any V in V, there exists a unique set of scalars C1 to CK such that V is equal to C1 V1 plus CK VK. Right? I mean, we know this already. We called this the components of V relative to that basis, right? So, I want you guys to notice something. If we were to apply T of V, this is the same as doing T of that linear combination that we just wrote. And by the linearity properties, this is equal to C1T of V1 plus, you could just keep this pattern going, CKT of VK. Okay? What does this mean? This means that if we know where T sends all of the basis elements or all the basis vectors, we actually know where T sends any vector at all. Okay? Let me write this down here because this is a super important fact. So, important. Once we know where T maps a basis, or maps, a basis, we can determine how t maps any vector. Okay, this is super crucial. This is why the linearity properties are important. It means that if we know what t does to a basis, we know what t does to anything. And this idea will come back later. Okay? So let's apply this really quickly to an example here. So example, let's look at the following linear transformation. This is going to take a polynomial, a second degree polynomial, and map it to a second degree polynomial. So let this guy be a linear transformation satisfying the following. T of 1 is equal to 2 minus 3x. T of x is equal to 2x plus 5x squared, and t of x squared is equal to 3 minus x plus x squared. First, let's find t of p of x for any p of x in P2 of R, and B, let's find t of a particular polynomial, 19 minus 6x minus 12x squared. Now, in order for us to solve this problem, it's important to realize something, okay? Why did they give us these facts? That t of 1 is equal to that, t of x is equal to that, t of x squared is equal to that. Because I want you guys to recall, so this is for part A, I want you guys to recall that 1x and x squared is a basis for P2 of R. So because up there they told us what t does to any of those guys, we should be able to find t of p of x for any p of x. So let's take a guy in there. Let's take any arbitrary guy. I'm going to call it a0 plus a1x plus a2x squared. Let's take this guy in P2 of R. What would t of that guy be? So t of a0 plus a1x plus a2x squared. How would you determine what t does to this? Well, here's the trick. Isn't it true that this is equal to, we're going to use properties of linearity here. Isn't this a0 t of 1 plus a1 t of x plus a2 t of x squared? All I did was I pulled a0, a1, and a2 out, and I used the properties of linearity to separate the additions. Okay, but I can now use the facts given in the problem, right? Remember, t of 1 is this, t of x is this, t of x squared is this. So this implies this is equal to a0 times 2 minus 3x plus a1 times 2x plus 5x squared plus a2 times 3 minus x plus x squared. And if we were to combine like terms, we actually end up with, let me write the answer on the next page here. This is equal to, combining like terms, 2a0 plus 3a2 plus, The other terms are negative 3a0 plus 2a1 minus a2 times x plus, and then we get 5a1 plus a2 times x squared. Okay, so that is the answer to part A. Okay, we just found t of p of x for any polynomial. So now let's do part B. Remember, they want us to know what t of 19 minus 6x minus 12x squared is. They want us to figure out what this is. But look, guys, this is just a0. The negative 6 is a1, and the negative 12 is a2. So I could just use the formula that I just figured out for the last part. So t of that polynomial is going to be, we actually just plug it into the formula that we just got. We get the following. We get 2 times 19 plus 3 times negative 12 plus, let me do this on the next line because it's going to take up space, plus negative 3 times 19 plus 2 times negative 6 plus 12, all times x. Again, I'm just using that guy. Now I'm going to use this guy. Plus 5 times negative 6 minus 12 x squared. And so this gives us the answer 2 minus 57x minus 42x squared. Okay, so what we just figured out is that when you plug this polynomial in, it sends to this polynomial. Okay, what we're going to do now is talk about a few useful properties of linear transformations. This is going to be a theorem. So let's let T be a map from V to W. Let's let this guy be a linear transformation. Then the following two things are true. First, T of the zero vector, and I'm going to specify this is the zero vector in V, goes to the zero vector in W. So T sends 0 to 0. What is the proof? So proof. What is T of the zero vector in V? We know that the zero vector in V is actually the same as doing T of 0 times V, where V is any vector in V. But this is the same as 0 times T of V, right? This is by property of linearity. And 0 times any vector is always the zero vector, but of course this multiplication is happening in W. So there you go. By linearity, T of the zero vector is the zero vector. Let's do another one. This guy says that T of negative V is equal to negative T of V. Okay, so T of the additive inverse of an element is equal to the additive inverse of where it goes. So what is the proof of this one? Well, what's T of negative V? We know that negative V is the same as negative 1 times V. But by linearity, this is the same as negative 1 times T of V, which is the same as negative T of V. Okay, so those two properties are extremely easy to prove. or to prove, and there you go. We've got some nice consequences, things that are true about linear transformations. The next topic in this section, we're going to be talking about linear transformations, in particular from Rn to Rm. Okay. So I'm not just going to write a theorem down. What I actually want to do is do a quick example for you guys, and then I'll loop back around and show you guys that we're going to completely classify linear transformations from Rn to Rm. So for this example, I want us to define T. This map is going to go from R2 to R4, and we're going to define it as follows. Okay. I just have to tell you where T sends an element. So where does T send? I got to send it an ordered pair somewhere, right? Because I'm sending R2 to R4. So this is where I'm going to send it. It's going to go to 2x1 plus x2, 3x1 minus x2, negative 5x1 plus 3x2, and negative 4x2. I'm hoping you guys all see that we took something in R2 and the answer clearly lies in R4, right? Because we've got four-dimensional vector, right? So two-dimensional vector to a four-dimensional vector. Okay, so this is a linear transformation. Let's do a quick verification that this is a linear transformation, okay? So verify that T is a linear transformation. So let's verify property 1. T of, we need to add two guys together. So it's going to be x1, x2 plus y1, y2. So if we add those two guys together, then that means that we're applying T of x1 plus y1, x2 plus y2. Okay, so that means that we need to plug those into the formula. So now this is like x1 from before, and this is like x2 from before in the definition. So what does this equal? If you go through it, it looks like this. This is equal to 2x1 plus 2y1 plus x2 plus y2, 3x1 plus 3y1 minus x2 minus y2, negative 5x1 minus 5y1 plus 3x2 plus 3y2, and then negative 4x2 minus 4y2. So that's just what we get by direct plugging in. But what does this equal? What we can actually do is separate these parts. In other words, if I were to write this, if I were to combine this guy and separate it out into two vectors, and then this guy, and I'm going to do that all over. I'm going to take this guy and this guy out, this guy and this guy out. I'm going to take this guy and this guy out, this guy and this guy out. Same thing over here, separate those two. We end up with the following. This is equal to 2x1 plus x2, 3x1 minus x2, negative 5x1 plus 3x2, negative 4x2. So those are all the single underlines, right? And then plus the same thing except with y1. 2y1 plus y2, 3y1 minus y2, negative 5y1 plus 3y2, and then negative 4y2. So all of this is just the same as t of x1, x2 plus t of y1, y2. Okay, so all of this was to check property 1 of linearity. Okay? Let me check property 2 now. What is t of a constant times x1, x2? This is the same as t of cx1, cx2. Plug those into the formula from before. This is equal to 2cx1 plus cx2, 3cx1 minus cx2, negative 5cx1 plus 3cx2, and then negative 4cx2. But I hope you could see that if we pull a c out, then this is just 2x1 plus x2, 3x1 minus x2, negative 5x1 plus 3x2, and then negative 4x2, which is the same as c times t of x1, x2. So why did we do all of this? To show that t is a linear transformation. Now, we are going to come back to this a little bit later, but important, I need to specify an important theorem here. This theorem is going to be the crux of, or the beginning of the foundation of all linear transformations from Rm to Rn. So theorem. Let's take any matrix and let's say that it's an m by n matrix. And we're going to define a linear transformation from Rn to Rm as follows. I need to tell you what to do to an element. So what does t do to a vector? It takes a and left multiplies it by that vector, okay? So in other words, a transformation takes the vector x and multiplies it on the left by the matrix. And what do we mean by a matrix times a vector? I need to specify here we are treating x like a column vector whenever we do this. Okay. What does the theorem say? T is a linear transformation. Okay. Before we do the proof here, let me just say, let me summarize what I'm saying here. We're saying that if we take a vector and left multiply it by a matrix, this is a linear transformation. Also, do the dimensions work out? Yes, because I want you to notice something. A is an m by n matrix. And X, remember, is an Rn, so this is actually an n by 1 column vector. And so when you multiply those two, your answer is going to be what? So the entire thing is going to be an m by 1. In other words, the answer will live in Rm, just as we say. Okay? So terminology before we go on. T is called a matrix transformation. Okay? So let me go ahead and prove this really quick, that this is actually a linear transformation. So let's start with two vectors, x1 and x2, that live in Rn. And let's take any m by n matrix. Okay? And also, let's take any scalar. So first, what would T of x1 plus x2 be? Well, this is defined to be matrix multiplication ax1 plus x2, but we know that matrix multiplication distributes over addition, so this is ax1 plus ax2, which is the same as T of x1 plus T of x2. So property 1 holds. Property 2. What is T of c times x1? This is equal to multiplying a times cx1. But we know by matrix multiplication that you're allowed to pull a scalar out and it doesn't change the result. So this is really c times ax1, which is the same as c times t of x1. Okay, so that is the proof. Okay, so here's what we have learned. We've learned that when you fix a matrix and you left multiply by that matrix and that's your map, that is a linear transformation from Rn to Rm, and we call that a matrix transformation. This is true for any matrix, okay? So if your matrix is m by n, it actually maps from Rn to Rm. Notice the swap there, so just be careful about that. M by n matrices go from Rn to Rm. Now, our next example is going to be a connection. Okay? So let me write the example down and you'll see what I mean by a connection. Let's call this guy T2. So I want T2 to be the map from R2 to R4. Let this guy be the matrix transformation. Given by the following 4 by 2 matrix. 2, 3, negative 5, 0, 1, negative 1, 3, 4. Okay, what does this mean? This means that T2 of any vector in R2 gets multiplied by that matrix. So question, what is T2 of x1, x2? Let's figure it out. T2 of x1, x2 is going to be the matrix I just wrote down, 2, 3, -5, 0, 1, -1, 3, 4, times x1, x2. How do you do a 4 by 2 times a 2 by 1? The answer is going to be a 4 by 1. This is going to be, let's see, we have 2x1 plus x2, 3x1 minus x2, -5x1 plus 3x2, and 4x2. What this means is that if we want to write it not in column vector form, this is what we get. Okay? Why did we do this example? Well, I want you to look really carefully at this guy. This is what t does to x1, x2. Does that look familiar? If we go back to our last example, where we proved that this was a linear transformation, you will notice that it is the exact same transformation. Okay, so this is really good. This is a really important connection. Let me write this down over here. Okay, so notice T2 is actually the same transformation as T from our last example. Why is that interesting? Well, in our last example, we didn't write T as a matrix transformation. We just wrote T as a generic transformation, and here we showed that it was really a matrix transformation. So a natural question arises out of this. So let me write this down on the next slide here. So natural question. Are all linear transformations T going from Rn to Rm really matrix transformations? Okay. Are they all that? The answer is yes. And this is why it's important, okay? This means any time that you transform from Rn to Rm, it's really just left multiplication by a matrix. So this requires a theorem. The theorem says, let T going from Rn to Rm be a linear transformation. And let's let E1 to En be the standard basis in Rn. Then T is really a matrix transformation. Using, I need to tell you which matrix it is, so using the matrix as follows. So this is the important part. The way that you find the matrix is you see what T does to the basis elements. So T of E1, this is going to be your first column. T of E2, this is going to be your second column. And T of En, this is going to be your last column. And I want you to notice something, that each of these T of something is an M dimensional, so there are actually M rows and N columns here. So this, of course, is an M by N matrix. Okay, A has a special name. A is called the matrix of T. A is called the matrix of T. So this is extremely important. What we're saying is that every linear transformation from Rn to Rm is really a matrix transformation. And to find the matrix of the transformation, you just have to apply T to the standard basis and make them all columns of your matrix. Okay, and that is how you do that. So let's do an example here. This will be our last example of the section. So let T, which goes from R3 to R2, be a linear transformation with the following. T of 1, 0, 0 equal to 4, 5. T of 0, 1, 0 equals negative 1, 1. And T of 2, 1, negative 3 equals 7, negative 1. Part A, find the matrix of T, and part B, find T of X for any X in R3. Okay. Now, we can almost find the matrix of T because they give us two nice facts here. We know that this is true and this is true. In other words, what they're telling us is, so we know T of E1, or I, is equal to 4, 5, and T of E2 is equal to negative 1, 1. The problem is we don't know what T of E3 is because they told us instead what T of 2, 1, negative 3 is. Okay? So what we need to do instead, assuming that they gave us three linearly independent things, what they gave us still forms a basis. And so what we need to do is figure out how to write. So we need T of E3. So the trick is going to be to write E3. So E3, which is 0, 0, 1, we need to write that as a linear combination of the ones that are given in order for us to figure out where T sends it. Okay? So we need to figure out what C1, C2, and C3 are in order for us to write it in terms of the other basis. So this is what we need to do. And actually, if we want to solve this system, this actually leads us to the following system. 1, 0, 0, 0, 1, 0, 2, 1, negative 3, and then 0, 0, 1. This is the system that we are trying to solve. The good news is this takes only one step. We're going to multiply row 3 by negative 1/3. So what is this equal to? We get 1, 0, 0, 0, 1, 0, and 2, 1, 1. And then we have 0, 0, negative 1. Negative 1/3. What does this mean? This means that C3 is negative 1/3. C2 is, C2 is 1/3. And C1 is 2/3. Okay, so now we can figure out what T of 0, 0, 1 is. So T of 0, 0, 1 is just going to be 2/3 T of 1, 0, 0 plus 1/3 T of 0, 1, 0 minus 1/3 T of 2, 1, negative 3. If you apply T to those, we know what they are because that's given in the problem, and then we multiply by what's there, we get the following. We get 8/3, 10/3 from the first one. The second one is negative 1/3, 1/3. And the last one is negative 7/3, 1/3. And this is equal to 0, 4. So all of this work was to figure out, in other words, that T of E3 is equal to 0, 4. So we're ready, right? Because we know what our three guys are. If we come back here, T of E1 is this, T of E2 is this, and T of E3 is this. So the matrix of T is, you just make those your three columns. So what are the three columns going to be? First one was 4, 5. The next one is negative 1, 1. And the last one is 0, 4. So this is the matrix of our transformation. Okay, that is how you do part A. Let's look at part B now. Part B asks us what T does to a general element. Okay, remember we are transforming R3 to R2, so we need to figure out what T does to X1, X2, X3. Well, we're just going to multiply this matrix that we got from before, because remember that is the transformation, by this column vector, and we could see what happens. Well, if you multiply this out, you get the following two-dimensional vector. This becomes 4x1 minus x2. The next one is 5x1 plus x2 plus 4x3. Okay. There you go. And so if we just write that not as a column vector, we get the following. 4x1 minus x2, and then 5x1 plus x2 plus 4x3. So we just figured out what T does to an arbitrary guy. So look, guys, every linear transformation, this is the moral of the story here, every linear transformation from Rn to Rm can be written in two ways. You can either write it this way, which is just telling you what it does to a general element, or you can write it in matrix form. That is the matrix form of the linear transformation. That's called the matrix of the transformation. Okay. Okay, as our last example in this section, we're going to be talking about an important transformation in R2. So what we are going to be doing is consider the mapping T from R2 to R2, which rotates a vector in the plane by an angle theta in the counterclockwise direction. Okay. So to give you a picture of this, what this is saying is that if you take any guy, let's say we take a guy x1, x2, which is sitting right here. So let's say this guy is x1, x2. What we do is we rotate it by an angle theta. So theta maybe is this angle right here. And so maybe the answer is right here. This would be T of x1, x2. Okay, so question, is this a transformation? Okay, the answer is yes. Okay, you can think geometrically about this, but basically what it's saying is if you were to rotate two vectors and then add them together, that's the same as adding the vectors and then rotating it, right? Because rotating a parallelogram is a parallelogram. And that's how we add vectors in R2, right? We draw a parallelogram. Also, if we multiply a scalar by a vector, that's just making the vector longer. So of course, if we make it longer and then rotate it, that's the same as rotating it and then making it longer. So it is a transformation. So, question, if we fix an angle theta where theta lives between 0 and 2 pi, right? We have to rotate it some angle between 0 and 2 pi. What is the matrix of the transformation. Because remember, every single matrix from every single transformation from Rm to Rn is really a matrix transformation. So what is the matrix of the transformation? Remember, we just need to figure out what T does to the standard basis. So what's T of E1? Well, think about it, right? E1 is this vector right here. That's E1. And we're rotating it by an angle theta. And the trick is to notice that if we take vector E1, which remember, that's the same as I, right? This is E1. If we take that guy and we rotate it by an angle of theta, because it has length 1, it sits on the unit circle, doesn't it? And so the answer, if that's theta, this guy is going to go to the point cosine theta sine theta, because that's exactly the unit circle, right? This is how we define the unit circle. So T of E1 is equal to cosine theta sine theta. Now, let me use a different color here. Where would this guy go? Because that's E2. So that's going to go to some other guy here. And we notice that these two have to be orthogonal, right? Because I and j are orthogonal. So if you rotate them both by theta, that's orthogonal as well. So what does that have to be? T of E2 actually has to be the following vector. It has to be negative sine theta and cosine theta. Okay, that is this point right here. So if we want to, put our different color here, this guy is negative sine theta, cosine theta. By the way, you could see that if you dot these two, you get 0. That's important because it is orthogonal. Okay, so we're ready to write the matrix. The matrix of T, just make those your columns, is cosine theta, sine theta, and then negative sine theta, cosine theta. Super interesting. This means that if we ever want to rotate a vector in R2 by theta, you just multiply it by this matrix. Thank you very much for watching this video.